This content is AI generated for informational purposes only and should not be directly used for clinical decision-making.
Hello and welcome back to the Neurosurgery Hub podcast. I'm Dr. Aris, senior attending here, and I'm joined as always by our research fellow.
And I'm Dr. Alara. Today we're looking at a fascinating new study from Scientific Reports titled A Cost-Sensitive Multiclass Machine Learning Framework for Postoperative Neurosurgical Triage, or as the authors call it, Neuro-TACTIC. This paper comes out of the Heidelberg University Hospital Group and was published in 2026.
This is a topic that hits home for anyone who has ever finished a long elective craniotomy at 5 p.m. and had to argue for an ICU bed. The decision of where to send a patient postoperatively, the regular ward, an intermediate care unit or IMC, or the full ICU, is a constant balancing act. We have to balance patient safety and early detection of deterioration against very real resource constraints and staffing ratios.
Exactly, Dr. Aris. The authors point out that many institutions still default to routine ICU admission after elective craniotomy. However, there's long-standing evidence that only a subset of these patients actually require ICU-level interventions. The problem is that most existing risk scores or machine learning models collapse this into a binary ICU versus non-ICU decision.
And that's not how modern neurosurgical departments actually function. We have IMCs now. An IMC patient might need closer monitoring than a ward can provide, but doesn't necessarily need a ventilator or pressors. This paper addresses that middle ground. Ilara, walk us through the methodology. How did they build Neuro-TACTIC?
They used a retrospective cohort of 1,072 patients who underwent elective craniotomy. They trained an XGBoost-based classifier using 27 different features. These features weren't just basic demographics. They included intraoperative data and imaging-derived features. Specifically, they looked at things like ACEs score, tumor volume, and even surgical positioning.
I think it's important to highlight those 27 features. For the residents listening, what were the heavy hitters in their model?
After running their feature importance analysis, 5 factors stood out as the most influential: operative duration, tumor volume, surgical position, body mass index or BMI, and patient age.
That makes perfect clinical sense. A 10-hour surgery for a large skull-base meningioma in a 75-year-old is a different animal than a 2-hour glide for a small convexity tumor. But let's talk about the cost-sensitive part of the title. That seems to be the core innovation here.
This is the most critical part of the study. In traditional machine learning, the model treats every mistake the same. But in neurosurgery, under-triaging, sending an ICU-bound patient to a regular ward, is much more dangerous than over-triaging, which is just an inefficient use of a bed. Neuro-TACTIC introduces a tunable parameter called zeta, or zeta. This parameter integrates resource-related and harm-related costs to adjust the balance between over and under triage.
So if I'm a department head and I know my ICU is at 95% capacity but my IMC has beds, I can theoretically tune the model's threshold?
Precisely. By adjusting zeta, the framework can be tailored to local staffing ratios or specific definitions of what constitutes an ICU-level event. The researchers assess this across repeated cross-validation and bootstrap analyses to make sure the behavior remains stable across those different cost settings.
Let's get into the results. How well did Neuro-TACTIC actually perform when it had to sort patients into these 3 tiers?
They reported their performance at a specific operating point, where zeta was set to 0.975. In the development cohort, they achieved an AUC of 0.67 and a weighted F1 score of 0.49. They also tested it on an independent evaluation cohort of 81 patients to see how it generalized. There, the AUC was 0.60 and the weighted F1 was 0.44.
Those numbers, 0.67 and 0.60 AUC, might sound a bit modest to some of our listeners who are used to seeing AUCs of 0.80 or 0.90 in binary models. Why the difference here?
It's a great point. The authors are very transparent about this. First, multi-class classification, sorting into 3 buckets instead of 2, is mathematically a much harder task. Second, they aren't just predicting a binary outcome. They are trying to model complex clinical decision-making that involves a lot of gray area patients. They describe Neuro-TACTIC as a methodological proof of concept rather than a finished clinical tool.
Right. And that independent evaluation cohort of 81 patients is quite small compared to the 1,000+ in development, which usually leads to a drop in performance. But back to those top features, operative duration and tumor volume. Did the paper mention how they handled the imaging data?
Yes, they specifically included imaging-derived features like tumor volume, which they identified as a major predictor of postoperative care needs. Larger volumes often correlate with longer surgeries and a higher risk of postoperative edema or hemorrhage, which would necessitate ICU or IMC monitoring.
Another interesting one was surgical position. We know that sitting position cases, for example, carry specific risks like air emboli or different hemodynamic profiles compared to supine or prone cases. It's interesting to see the machine learning model pick up on that as a triage determinant.
Absolutely. And even BMI and age play a role in the frailty aspect of recovery. The model is essentially trying to weigh the surgical hit against the patient's reserve.
Now, let's talk about the limitations. As much as we love the idea of an AI telling us where to send patients, the authors were quite cautious in their conclusions, weren't they?
They were. They explicitly stated that prospective validation and multi-center evaluation are required before this could ever be deployed in a clinic. The study is retrospective, meaning it's looking at what surgeons did in the past rather than necessarily what the ideal triage would have been. There's always the risk that the model just learns the existing biases of the surgeons at Heidelberg.
That's the ground truth problem in AI. If we've been over-triaging for years, the model might just learn to keep over-triaging. But the cost-sensitive zeta parameter seems to be their answer to that, giving us a knob to turn to correct those biases.
Exactly. It allows for asymmetric costs. If a hospital decides that a single missed ICU level event is 20 times worse than one wasted ICU bed, they can set the zeta to reflect that. It makes the model much more flexible than the rigid, older scoring systems like the ASA or simple regression-based tools.
So for the residents listening, the takeaway here isn't that you should stop using your clinical judgment and look for an app. The takeaway is that we are moving towards a more nuanced, three-tier understanding of postoperative care. The ward versus ICU binary is dying.
And the inclusion of the IMC level in Neuro-TACTIC is a huge step towards reflecting how we actually practice. The researchers demonstrated that it is at least feasible to model this three-tier triage using demographic, intraoperative, and imaging data.
It's a glimpse into the future of precision triage. If we can use Neuro-TACTIC to identify the 30% of patients who truly need the ICU, we can provide better care to them while not overwhelming our staff with patients who could safely be on the ward.
And that's a win for both patient safety and hospital economics.
Well, that's a great place to wrap up. A very interesting study from the Heidelberg Group. Neuro-TACTIC is definitely a framework to watch as it moves towards prospective trials.
Definitely. Thank you for the deep dive, Dr. Aris.
Thank you, Alara. And to our listeners, thank you for joining us on the Neurosurgery Hub podcast. We'll see you in the next episode.
Goodbye.